Now we'll move to the second part of our three, and that's the object. And when we talk about color, that's the thing we're talking about color about is the object. We need to see something that has to have a color. So the term we use to mathematically describe it is called the spectral reflectance curve. This curve describes the object in terms of the amount of light energy that is reflected at each wavelength in the visible portion of the spectrum. So now we're talking not about light that's generated from a source and comes out, but light that hits the surface and bounces off. One thing about objects, and the thing that makes them different colors, is that when light hits an object and is reflected, which wavelengths of light are either absorbed or reflected determines the color. So you can think of an object that has color as selectively absorbing and reflecting different wavelengths of light. So if an object appears to us as blue, that means it's reflecting the blue part of the spectrum and absorbing the other colors, so that it doesn't come back and we don't see it. So essentially it's taking away all the colors except for blue and allows us, it reflects blue, that's why we see blue. Colorants are materials that can selectively absorb or reflect certain wavelengths of light. And depending on which ones they do, they appear as those colors. The higher the graph, the more light of that wavelength is reflected. So some colorant, we'll see as we get into color a little bit more, we'll use a spectrophotometer to give us an object curve. And if an object curve is very high, that tends to mean that it reflects a lot of light. If it's low, it doesn't reflect as much light. So the higher one would be lighter, appear to us as a lighter, brighter, more chromatic color. If it's low, it'll tend to be a weaker, duller, darker color. We'll see that as we go on through the class. Okay, optical properties of an object are linked to its structure of material of that object, and it has to do with chemical bonding and crystallinity, all that stuff that you're all very interested in. You've had the intro class, you've heard those terms before. We're not going to get into it too much, but it involves the way the material interacts with light, and there are several things that light can do with an object. So it has to do with how the light passes through an object or is diffused by it, which means how it interacts with it. If it's transparent, the light will pass through and nothing will happen to it. If it's opaque, the light will hit it and it won't pass through. Those are too extreme, and then kind of can be in between. Light is reflected from the surface in different ways, depending on the texture of the surface. So that affects how it appears to us. And then also the color of that object affects how it interacts with light. So when we talk about what we talk about in industry with color, we actually talk about two things, color and appearance. When I talk about the Society of Plastic Engineers division that is involved with this course, it's called the Color and Appearance division, because there's color of an object, but there's also appearance, and those two things aren't exactly the same. Color is a part of appearance, but it's not the only part. So an object can transmit light, so the light hits its surface and goes right through it. Think of anything that's clear, but clear plastic that doesn't have any color to it, it allows all the light to pass through it, so it's completely transparent and has no color. If, for instance, it transmitted the blue light but absorbed the other colors, then it would be transparent, you could see through it, but it would have a blue color. If somebody had a 7-Up bottle, it's transparent, you can see through it, you can see the pop that's inside, but it also has a green color. The way that dye, in that case, works is that it reflects, or it doesn't reflect, it transmits the blue or the green wavelengths, and it absorbs the other color wavelengths, so all we see is green. It also can absorb either all the light or certain wavelengths of light. If an object is completely black, like this chair here, that is absorbing all the wavelengths of light. An interesting thing to see if you work in a color house and they have their pigments in big barrels, if you take the top off a barrel of black and look inside, you can't see where the bottom, you can't see the the bottom because none of the light is reflected. So you can't tell how full it is because you just can't see anything in it. It's completely black because all the light is absorbed. You don't see it. It can also scatter light, so light can hit it and bounce off in different directions. And it can be a combination of all of those. And plastics generally are a combination. They're somewhat translucent. Transparent. An object is considered transparent if it has the ability to allow the incident light to pass through it without being scattered or reflected. So if it's a truly transparent material, it's very clear. Think of a piece of glass that's transparent. Clock, yep. And in that case, it doesn't selectively absorb any wavelength, so it appears just completely clear. And there's a lot of plastics that are like that. Polystyrene, acrylonitrile, polycarbonate. Those are all very transparent materials. And generally speaking, this is a little off subject here, but we can color those with dyes, which are also very transparent, and it can make for a very clear, transparent, colored plastic part. Think of taillight lenses. Those are red. It's very critical exactly how red it is, because there's standards for that. But it's very transparent. Just got the light behind it to shine through. It has the ability to capture the incident light and not transmit or scatter the light at all. Again, on the extreme, if it's a black, opaque object, all the light that falls on it is absorbed, so none of it is reflected or transmitted. So it's absorbing that energy. Light is energy. So what do you think happens when light falls on it and absorbs all that energy? What happens to the temperature of that object? It goes up, right? So that's why if you have a black car and a white car out in the sun, the black car tends to get hotter inside faster than the white car, because the white car is reflecting that light off of it, so it's not absorbing it, but producing heat. Black absorbs all that heat, so now it becomes hot. So light is just a form of energy, and energy can be turned from light into heat. Scattering is the ability of an object to reflect incident light in many different directions, different from the direction of incident light. So it hits it, and it can go in any direction you would imagine. And that's called scattering. Scattering is affected by a property called refractive index, and refractive index is defined by, and you'll love this nice scientific description, equal to the speed of light in air, strictly speaking, a vacuum, divided by the speed of light in the material. Air has a refractive index close to 1. So when light passes through air or a vacuum, it goes at a certain speed. When light passes through a block of polystyrene, it goes at a different speed. The difference between those two speeds is measured as the refractive index. The effect of the refractive index on the speed of light, you all remember that light travel is at 186,000 miles per second. And if it goes through a different material, it goes at a slower rate generally. So let's say that light goes through this block of glass, which has a refractive index of 1.5. When light goes through the glass, instead of going 186,000 miles per second, it goes at 124,000 miles per second. And if we divide 124,000 by 186,000, we come up with this reactive index of 1.5. And when it comes out, it goes at the fast speed, which in itself isn't very important. But how that affects color is kind of what's important. So what happens is, as the light hits an object, it's on this angle, it goes through the material, and it actually changes the angle because it goes through at a different speed. Some of this light is reflected off of the surface, and you can measure all that stuff and get all kind of equations and that sort of thing, which we won't worry about. But if you look at this and see how that's been, think of an everyday situation where you might have seen this in action. Say you're by the side of pool, say, and you have a stick. If you stick the stick in, place the stick in the water, and you look at it underwater, what's it look like? Does the stick go straight through, or does it look like it's bent? Looks like it's bent, right? And that's sort of what's happening here. The light travels at a different speed, so it looks like it's actually bent, which it's not. It's just how the light makes it to our eyes is a little different speed, and that causes it to look different. That can affect how colors work also, as we'll show here. Okay, what's important for colors and colorants and pigments generally is that if the refractive index of the material you're coloring, plastic, and the refractive index of the colorant you're using to color it are very close together, you don't get much scattering. The more scattering you get, the more color value you get, the stronger the colorant. What you want is to have a pigment, colorant, that has a refractive index that's somewhat different than the material that you're coloring. Because if it's different, it doesn't matter which direction it's different, whether it's higher or lower. If it's different, you get more scattering, and you have a stronger color. So that's one thing a lot of colorists don't realize in strength is that, for instance, a colorant may have a different strength in one material than it does in another because of the difference in the refractive index. That's not a huge difference, but it can be important in certain applications. Where this comes into effect, too, is in biology. If you're looking at cells in a microscope, usually they're in some kind of medium. So if the medium you put it in, water or salt solution or something, has the same refractive index as the cells you're looking at, you don't see it very much. There's no contrast. Hard to distinguish. But if they're different, then you can see the difference easier because of the way the light is reflected differently by the different refractive index. But you get into physics and that fun stuff, you'll get into it more particular, but for our purposes, this is what's important. The more different the refractive index is between the medium you're coloring and the colorant, the more color strength. And when you're working with colorants, you're always interested in color strength and using less color to get the same results because color is usually expensive compared to other things. So you always want to use as little as possible. For those of you that are in industry, what's the most important thing? The bosses are always saying production and make it less expensive. Yeah. And the reason they say speed it up is because it costs less per unit made. If you have machine costs, say that's a cost per hour. If you make 100 parts per hour, it costs you less per part than if you make 50 parts. Okay, so this is another picture that shows what we talked about. If the particles in the medium have the same refractive index, the light will pass through it and don't have much scattering. If they have different refractive indexes, then you get scattering. If you looked at, if these were two different red samples, this one would be more transparent than this one. You have scattering, so it'll look a little cloudier. So it also affects transparency. The particle size is very important when we talk about pigments. We'll talk about dyes and pigments as different colorants. It's really only important for pigments. So the particle size of the colorants also affects scattering. Very small particle size scattered little light, so you don't get much color strength. Although in practice, it's very difficult to get them so small that they're at this point. They're usually bigger than that. Scattering increases with increasing particle size until the particles are as large as the wavelength and decreases as it gets larger. So the most efficient size for the particle of a colorant is the size of the wavelength. Again, that's pretty small. We're talking about really small particles. So it's in practice, it's actually tough to get that small. So we have a graph. We always like graphs in science and math. So here's a graph. So this shows on the bottom the particle size. So as we go to the right, the particle size gets bigger. And as we look at the graph on the left side going up, the higher the graph, the more scattering you get. So there's an optimum size where this dashed line is that is the optimum for scattering. So if you had a perfect world and you could make all the particles the same size, which you can't anyway, but if you could, you would make all your pigment particles exactly this size, whatever that number would happen to be. Depends on what color you're after and what wavelength that particular color is. So if we go to the right and get larger, the amount of scattering and the coloring strength goes down. And if we go to the left, it goes down also. Realistically, very seldom, if ever, do you ever get to that point. So what we generally say is the smaller the particle size, the better the coloring strength, better the scattering. That's true in most cases unless you're right here, which practically doesn't happen very often. So you want, and we'll talk about this in more detail later, but the smaller you make the particles, the stronger the coloring strength of the material. And it has other effects too. So particle size is very important when we talk about pigments. Pigments are most efficient as light scatterers when their refractive index is quite different from the resin in which it is used, and the particle diameter is about the same size as the wavelength of light. That would be the optimum. Okay, we can also have translucent material, and in this case, the object has the ability to allow the incident light to be transmitted, absorbed, and scattered at the same time. So many plastics are translucent. Think of high-density polyethylene, which we make milk jugs out of. Look at it, it's translucent. It's not really transparent. You can't really, if you had something behind it, you couldn't see it very clearly, but you could tell that there was something there. That's what we mean by translucent. And there's varying degrees of translucency also. So of all possibilities, translucent, opaque, or transparent, translucent is the most complicated. It has the most things going on. Most difficult, actually, for a spectral photometer to give you good numbers on it. We could also have something called fluorescence. I think everybody knows what a fluorescent colorant looks like. A lot of kids' stuff these days are fluorescent. Kids like fluorescent stuff. The optical effect is the result of the ability of a colorant to absorb radiation, usually in the ultraviolet region, and then to immediately emit it as a visible light of a longer wavelength. Showing a picture here, and what it's showing is that this is the color of the light, and it's coming out as a different color, basically. Transmittance, the ratio, a couple definitions here. The ratio of transmitted light to the incident light under specific geometric conditions. Basically telling you how much light is transmitted compared to what hit it. And reflectance is the ratio of reflected light to the incident light under specific geometric conditions. So you can measure transmittance and you can measure reflectance if you so desire to do that. Specular reflectance is a reflectance that excludes diffuse reflection as in a mirror and does not produce color. If you think of back in the old days when they used to have chrome bumpers, and say you were driving and the sun was behind you and there was a car with a bumper in front of you, if the light hit that bumper exactly the right angle, that the light from the sun would go directly into your eyes and you would be, a glare would come from, right? You've had that pleasant experience, right? That's specular reflectance. That's actually a mirror-like reflection, as it says, as in a mirror. The light hits the object and is completely reflected and isn't affected by the color of the object. It happens mainly with shiny things. If I had a shiny piece of plastic and these lights were all on and I turned it, you would see the reflection of the light. For you guys over here, you can see the shiny part on that mouse there. I can see it from here. That's the specular reflectance. And it only happens in exactly the right angle where that light hits it and bounces directly into my eye. if I move here, that specular reflectance moves, or that light that I see moves a little bit. It has to be in the right angle. Okay, and that can affect appearance quite a bit, and we'll talk about that later on in the course. And diffuse reflection or reflectance is the reflectance that excludes the specular reflectance, and that's what produces color. So we really have two types of reflectance off of the surface. Diffuse, which comes off as the color of the object, and specular reflectance is really just a mirror-like or exact replica of the light source itself and does not have color to it. So if you happen to be looking at that angle and there's a bright light, it'll look like glare. There's another way of describing it. You don't see color, you just see basically the light source. So specular reflectance comes off in a very specific way, or a very specific angle here. Is this specific color, whatever it may be, has a very specific spectral curve associated with it. Okay, and these happen to be ink samples. But one thing we can use spectral curves for when we get them from the spectrophotometer is to identify, for instance, which colorants make up a mixture in an unknown sample, because it has a very specific structure to it. This little hump here is indicative of a very specific pigment called phthalo blue. And as we get into some more areas, you'll see that more specifically. Here's a red. Now the red, if we look at our spectrum colors underneath it, we'd see this is where the red part of the spectrum is. Where it goes up is what's important. And we see it's absorbing all the light up until that wavelength. So it has a very specific shape to it for a specific color. Here is magenta. And magenta has a red area, but it also has a blue area. So it's a combination of red and blue. Green, we have our hump in the middle. Remember, about 550 was the strongest part of our eye for seeing color, and that's where the green falls. So we have a hump in the green, absorbs in the blue, and absorbs in the red. Yellow looks like that, sort of like the red, but it starts earlier. And there's a blue, a dark blue. It has a hump there, and since this is a darker color, notice that the size of the curve is much lower than it was in the other one. And that's a black. Black would be straight across on the bottom here. And notice it's not perfect black. If it was perfect, it would be 0 all the way across. If we had a perfect white, which there's no such thing as a perfect white, where would the line be, you think? What would it look like? It'd be at the 1 all the way across, right? It would reflect all wavelengths perfectly. But we don't have pigments that work that much. Here is kind of our closest approximation to a perfect white, and that's if we measured a piece of paper, white paper, and we use a chemical called TiO2, or titanium dioxide, as a white pigment. It's the most common pigment used in industry. It's white, very strong, very good reflection, and also fairly inexpensive. But this curve, somebody that understands or knows curves would be able to tell you that's TiO2 because of this dip right here, this absorption area here, because it's not quite straight across. Again, when we get into talking about the curves a little later, we'll see how we can identify colorants by the curve. Another definition there, gloss, angular selectivity of reflectance involving surface-related light, responsible for the degree to which reflective images may be superimposed on a surface. Kind of a long, wordy definition, but gloss, think of it as shiny. Something has a lot of gloss if you look at it and you can see the reflection of an object in it that looks clear, like a mirror. Think of a mirror would be perfectly glossy. Understandable definition, hopefully. Haze is a scattering of light at the glossy surface of a specimen responsible for the apparent reduction in contrast of objects viewed in the reflection. So if it's not as clear anymore, that image of the reflected image or reflected object that you see is now not so clear anymore. Now it's kind of hazy, kind of wavy. You don't see it as distinct anymore. That's considered haze. So as more hard it is to see the object, the more hazy it is. Okay, smooth surface reflection. Specular reflection of light from a mirror-like surface works like this. The incident beams hit it, and then it bounces off, and if you measure that, it looks like a 90-degree angle. Okay? If that's what a smooth surface does. The important thing here is that the light hits and all the light goes in one direction. It's not scattered in other directions. It just all goes in one direction. If it's a rough surface, matte finish we call it, little bumps in it. Now when the light hits it, some of it goes in this direction, some of it goes in this direction, some of it there, so forth. All goes in different directions. We don't see it only in one direction. It's spread out. That's why a rough surface doesn't appear as shiny as a shiny surface. And if we superimpose now that on it, the combination of diffuse light and specular reflection due to the scattering from beneath, that's how we see an object. There's light that's coming in a diffuse manner. In this case, say it's a red object. And then there's also the specular reflectance, and this happens to be a shiny surface or a smooth surface, so all the light goes in one direction. So we would see it as red in every angle we look at it, except if we look in this angle, all we'll see is the light. It'll be glare looking in that area. We'll see a reflection of the light. Won't see the red color, but as soon as we move off that angle, then we see the red again.